Okay, hello everybody. Welcome to the second tutorial. So today we're going to start quantum mechanics. You have done, during your undergraduate levels, you've done 2 courses in quantum mechanics, but you've never gone beyond one particle. So everything you've solved up till now was actually really simple and really stupid, because you only had one single particle in some kind of potential, some kind of system, and then you solved Schrödinger equations, did whatever you did. But you never have more than one particle, which means that you never actually try to think what happens when 2 particles interact. So electrons have a charge, there's Coulomb interaction, obviously that must have some effect. And the only time that you actually did deal with many particles, as in statistical mechanics, or statistical physics, you always dealt with an ideal gas. And an ideal gas, by definition, is a gas without interactions. So you're back to the single particle problem. You just have to do it 10 to the 23 times, but it's always the same problem. And even when you had interactions, you might have done mean field theory, which basically means take all of the particles, turn it into some potential, and you're back to one particle. So you've never actually done things that involve more than one particle, which is quite surprising. It's, you've been 3 years in physics and you haven't done anything real yet. So this is what this course is about. This is what field theory is about, quantum field theory, and the tool that deals with this kind of stuff is called second quantization. So let me start by stressing something that causes a lot of confusion. Everything you did up till now is what we call first quantization. What we're doing now is called second quantization, but there's no additional thing that we're quantizing. So the energy levels are already quantized. They're already discrete. We cannot quantize them again. So there's no such thing as first and second quantization as it sounds. It's just a name, which doesn't really mean anything. So don't get confused. Okay? It's just the name of what we're going to do. As soon as you start writing quantum states in terms of creation and annihilation operators, this is called the formula of second quantization. But we're not quantizing anything in addition to what was already quantized. So that's that. So if we're talking about a many-body system, what is the ground state? No matter what the system is, no matter what the energy is, no matter what the interactions are, the ground state of the system is that you have 0 particles. If you have no particles, the energy is at a minimum. And this ground state is what we call the vacuum. And we write it as a ket with a 0 inside. This is called the vacuum state, and it is the ground state one C, 2 U's. It's called and it's the ground state of a many-particle system. Now you want to start putting particles into the system, so we can use the creation operator. And what this creation operator does is it creates a particle out of nothing, and it creates it in the state I. And this state I is a shorthand notation for a bunch of quantum numbers. So it creates a particle in the state lambda I. So these are a collection of quantum numbers. So this could be, for example, a 3-dimensional infinite potential well. In this case, you have 3 quantum numbers, nx, ny, and z. And now I'm creating a particle in state lambda I. So for example, this could be the state nx equals 1, ny equals 1, and nz equals 1. So when this operator acts on the vacuum, you then get one particle in the state I, so you have I minus 1 zeros, so there's 0 particles in state, in whatever state, and only in state number I, there is 1 particle, and all others are also 0. So in a way, you could say that the vacuum state is just a row of all zeros. There are 0 particles in each state. Now I've created 1 particle in state I. If I act with this operator a second time, then you create a second particle in that state. Let's say for the moment that we're using bosons, so we don't have problems with no Pauli exclusion. We'll get back to that in a minute. So in this case, you create another particle in that same state. The square root 2 is for normalization. Similar to ladder operators from quantum mechanics 1. So now I've created 2 particles in state I, and all other states are still empty. The same way I can use, say, another operator. Say I use a J dagger, where J is different from I. So now I want to create another particle in a different state. So, and this, let's say, is acting on this state. So it'll act on 0. And now I create a different particle, so I'll get a bunch of zeros, then the 2 at the ith position, a few more zeros, and then a 1 at the jth position, and so on. So the neat way to write this, obviously, if you're talking about a system like an infinite potential well, this can go on forever because there are an infinite number of bound states in an infinite well. It could also be finite if you're talking about a different system. But you don't want to write out the entire thing, so the usual way to write down states is by just writing explicitly the creation operators acting on the vacuum. So this state that we just created one by one, you can write this as, what did we do? We acted with AI dagger twice squared, and we have to divide by square root 2 to get rid of this for normalization. And then we acted with a J on the vacuum. And when you do this action, you apply all operators to the vacuum, you end up in this state. And this is what is called a Fock state. What about annihilation? So how do you get rid of particles? So here you have the complex conjugate. The operator A acting on state I. And if you apply AI, say, on the state with the 3 particles, then again you get a square root 2 for normalization, and then you only have 1 particle left at the ith position. what happens if I act on this state, not with AI, but with a K, where K is different from I and J. So I'm trying to annihilate one of these zeros. You obviously get 0. You don't get, it's not the state 0, it's not the vacuum state, it's the number 0. And this is actually the definition of the vacuum state, that for any I, when AI acts on the vacuum state, you get the number 0. That's how the vacuum state is defined. No matter which annihilation operator you apply, you always must get 0. Okay, so let's talk, bless you, specifically about bosons. And then we'll solve a question on bosons, and then we'll talk about fermions and solve a question about fermions. So in general, in a bosonic state, you have n1 particles in state lambda 1 and n2 particles in state lambda 2, and so on and so forth. So the way you write the general Fock state, because it is n1 particles in the first state, n2 particles in the second state. And the easy way to write this using the vacuum is a multiplication over all states I, AI dagger to the power ni divided by square root of ni factorial, acting on the vacuum state. So now you're creating n1 particles out of the vacuum in state lambda 1. You're creating n2 particles in state lambda 2 out of the vacuum, and so on and so forth. So this is how you create them one by one, and the wave function is normalized. The operators satisfy commutation relations, which are exactly the same as you had in QM1, and now you have indices. So they only, if I is different from J, they commute. Otherwise, the commutator is equal to 1, and all the operators of all the commutators of the same operators, so A with A and A dagger with A dagger, they always commute. So the only ones that don't compute are AI and AI dagger for the same index, for I, so the same I. This is what we call the algebra of the operators. Let's solve a question. We're going to consider a bosonic system with 3 levels, which I call lambda 1, lambda 2, and lambda 3. Because these are sets of quantum numbers. And what I would like to do, so the system is in the state n1 equals 2, n2 equals 0, and n3 equals 1. So 2 particles in state lambda 1, 0 particles in state lambda 2, and 1 particle in state lambda 3. And I would like to act on this with the annihilation operator. And I'm using a rather simple example to demonstrate to you how to use this algebra and the definition of the vacuum. So the fact that when an annihilation operator acts on it, you get 0. I'll demonstrate from this example how to do it, and then it'll be obvious how to do it for any more complicated state. So basically what we're asked to do, start from a different place. First of all, let's write our state in the general way of writing Fock state, so with the creation operators. So there's, I just plug in N1 to N3. So we have A1 dagger squared over square root 2, A3 dagger acting on vacuum. That's how I write the state with creation operators. And we are asked to evaluate AI acting on 2, 0, 1. And for simplicity, I will call this state psi. So we have a name for it. So how are we going to do this? So the state psi is equal to 1 over square root 2 AI acting on A1 dagger, A1 dagger, A3 dagger, vacuum. Right? That's what I have to evaluate. It's exactly this expression, but I've plugged in the Fock state. Now we can stare at this for a million years and not know what to do, but there's an easy trick. And the trick is that we somehow want to get the annihilation operator to the far right. If we can do this, if we can somehow move this operator to here, then we can use the definition of a vacuum, and it's equal to 0. Right? We know how to act with the annihilation operator on a vacuum. So we somehow have to get this operator to the end. Well, we can't just move it there. We have to use commutators because these things don't necessarily commute with each other.
Why can't we just lower the indices? Use the annihilation operator on the state that we have, for example, like 2, 0, 1 to lower it to 1, 0, 1.
So that's obviously what's going to happen, right? I'm demonstrating to you that this is actually what happens, and it's given by this algebra. Save your question when we get to fermions, okay? Because then it won't be so simple. So how are we going to move this through? So we can use the commutation relation. So first of all, you have to move it step by step. So step number 1 is moving it here. This is step number 1. In order to do this, we use the commutator AI-A1 dagger, which is AI-A1 dagger minus A1 dagger AI. This is equal to delta I1, which means that this order, AI, A1 dagger, that is equal to delta I1 plus A1 dagger AI. I'm going to plug this into here. So psi is equal to 1 over square root 2. Then the first expression is delta I1. And then there's an A1 dagger, A3 dagger 0. And the second expression, 1 over square root 2, A1 dagger, AI, A1 dagger, A3 dagger. So as you see, we've succeeded on moving the annihilation operator one step. 2 more to go. We've moved to 1 step. And we got an extra term, which is free of annihilation operators. Now we can do the same thing again. We can replace this product by the same commutator again. So we get another delta I1 plus A1 dagger AI. And we'll get another extra term, which is exactly the same as this term, the one with the delta. And the third term that will come out of here will have the annihilation operator moved another step forward. Let's do that. Psi is equal to square root 2 delta I1 A1 dagger A3 dagger 0. That's the 2 terms that we had that have a delta. And then there's one more, 1 over square root 2 A1 dagger and another A1 dagger AI and A3 dagger. Okay, almost there. Same trick again. And then there's a plus 1 over square root 2 A1 dagger squared delta I3. Let's move the delta to the beginning. Delta I3 acting on vacuum. And the last term is 1 over square root 2 A1 dagger squared A3 dagger AI vacuum. Okay, so we've done it. It's on the far end. This is equal to 0 by definition. And this means that we can now write it in an easier way to read. For I equal to 1, this delta is 1, this delta is 0. So you get square root 2, 1 particle in state 1, 0 particles in state 2, and 1 particle in state 3. If I is equal to 2, both deltas vanish, you get a 0. And if I is equal to 3, you're left only with this term, 1 over square root 2. 2 particles in first state, and then 0 and 0. Perfect. So as you already mentioned, this is of course what you would have expected. Of course, there's also things, there are constants beforehand, but if you know what you're doing, you could have guessed them as well. So this is not very new. But what I would like you to take from here is that all you need in order to do these computations is the algebra of the operators. They automatically lead to what you know intuitively to be right. Okay, what about fermions? This is where it gets complicated. Fermions are amazing creatures. So in this state, we have what's called the Pauli exclusion principle, which means that all v and i's, for all I, you can never have more than 1 particle in a state, either 0 or 1. There's no option to have more than 1 particle in a certain state. It technically makes the Fock states easier to write because there's no normalization because, right, this n is either 0 or 1, and factorial of 0 or 1 is 1, and square root of 1 is 1. I'll be using in a second. So you have an AI dagger to the power ni acting on 0. So if there is one particle in, say, state number 1, you act with it once. If you have 0 particles, and something to the power of 0 is 1, so there's no action at all. You don't create a particle. And that's it. There was a question?
When we wrote the site, we chose arbitrarily the order 1 and 3. I mean, 1, 1, 3 with the order 3, 1, 1 over.
Correct. And for bosons, it's irrelevant. For fermions, it's not. Okay, that's why fermions are more complicated. For bosons, it doesn't matter, and if you don't believe me, try it. Okay, you just did it?
Just mathematically, if we apply the creation operator again on a state that already has a particle in it, do we get the 0 ground state or 0, the number per se?
You get the number 0. And
annihilating the vacuum.
Correct. Correct. And as you will see, this is actually my next point, or not exactly that, but this is the. Let me make my next point, and then I'll tell you what I mean. So now the operators don't satisfy commutation relations, but what we call anti-commutation relations. There are different types of symbols out there in the world. So my symbol is curly brackets, and this is a symbol used in most textbooks. Some textbooks, and I think also Efrat, they use a plus next to square brackets, right? She uses both. Okay, so I'm going to use curly brackets, and what this means, of course, is AB plus BA. So I'm going to use curly brackets all the way through. It's what most textbooks use. Not all of them, but most textbooks use this. So now they anti-commute, and the same thing goes for, so if it's twice the annihilation operator, it's equal to 0, and also twice the creation operator is equal to 0. What you can prove, who asked the question? Yes, question. What you can prove in about half a line of math is that these anti-commutation relations, specifically this one here, leads to the fact, leads to Pauli exclusion, mathematically. So Pauli exclusion is built into the algebra of fermions. This again is the fermion algebra. That was the, when we had the boson algebra, and this is the fermion algebra. I didn't write boson. Boson algebra. Yes?
The only difference I see between the algebras is that you use curly and...
Correct. A curly brackets means that there's a plus sign, and square brackets means there's a minus sign. Right, you know what a commutator is? It's with a minus sign, so that's the only difference. Yeah, you're right. This is AB minus BA, and this is AB plus BA. That's the only difference. It seems harmless, right? The physics isn't that minus sign. People told you that minus sign is irrelevant, so I'm telling you it's not. The entire world changes if you add a minus sign. So let's solve some examples to demonstrate what's going on. So we're gonna think about a three-state system again. This time it is in state 0, 1, 1. These are now fermions. There are 0 particles in state lambda 1, 1 particle in state lambda 2, 1 particle in state lambda 3. And I would like to act on this with the annihilation operator. And the question is, what do I get? And as before, I'm going to call this psi. So we have a name for it. So I'm going to create 2 particles from the vacuum, one in state 3, one in state 2. That is the state 0, 1, 1. And now I'm going to act on it with the annihilation operator. But this time, and the trick is the same trick as before, what I want to do is I want to move the annihilation operator to the far right. I want to move this all the way here. Of course, I'll have to do it step by step. I have to move it here first, and then here. In order to do that, I have to use the anti-commutation relation, namely AI anti-commutes with A2 dagger. So this is AI A2 dagger plus A2 dagger AI. And this is equal to delta I2. I can shift around the terms, and this is delta I2 minus A2 dagger AI. So now when I act, so I now can do the first switch. I'm replacing these 2 operators with this expression here. So first term is delta I2 A3 dagger acting on vacuum, and then minus A2 dagger AI and A3 dagger acting on vacuum. Do the same thing again with AI and A3 dagger. So we get delta I2 A3 dagger 0 minus delta I3 A2 dagger 0. And then I have another minus sign that's in total a plus sign. A2 dagger, A3 dagger, AI, 0. So I've again used the commutation relations, or better said, the anti-commutation relations. But in general, it's the same idea. The only difference is that while the previous expression only had plus signs, no matter what stage we were at, here you sometimes get minus signs. You have to be very careful to figure out when you get minus signs, when you get plus signs. Which place? So what I did here is I replaced this expression, these 2 operators, by delta I3 minus A3 dagger AI. Right, so one term is the delta times A2 dagger, and the second expression has 3 operators. See it? Okay, so now we can again, this obviously vanishes. That's the definition of the vacuum. And let's write this in cases for I equals 1, I equals 2, and I equals 3. So for I equals 1, both deltas vanish. And we get the number 0. For I equals 2, we get A3 acting on 0. This is the state 0, 0, 1. And for I equals 3, we get minus 0, 1, 0. That's how you use anti-commutation relations. Questions so far? Okay, this was simple. It's the size of pi. So if you do this to one of them in an experiment, this leads to destructive interference. It's a big difference. It's the difference of single particle, not single particle. So the implementations in experiments in the lab go very far, and to actually see experiments, we'll have to learn a little bit more, to describe real experiments, because this is still a very simple system with no interactions. But when we'll get there, hopefully I'll show you some experiments as well and how bosons are different from fermions. Did I show you anything in solid state? I didn't show you anything. I'll bring you some nice experiments in the future, so you can look at them. Okay, let's solve one more example for fermions. Let's consider a two-level system with the states lambda 1 and lambda 2. And what I would like to do is I would like to write the matrix representation for the creation operator of state 1. So A1 dagger. Remember that operators are matrices. I hope that's not new for anyone. So when we write matrices for operators, what's the first thing we have to do? We need a basis, right? So we need to figure out what are our basis states. So we have a two-level system of fermions. So how many basis vectors are there? Watch out. Who's this 2? No one. Who's this 3? Who's this 4? Who's this 5? Who's this infinity? Okay, you're all quiet. No, these are the two states. This could be spin down and spin up. This could be any two states. Spin is included. Only two states. What are the two states? What are the states? No, that's the single particle states. I have a two-level system of fermions.
Depends on the number of fermions.
Aha. Number of fermions can vary. So I can have 0 fermions. 0 particle in state 1, 0 particle in state 2. I can have 1 particle in state 1 and 0 particle in state 2. I can have 0 particles in state 1 and 1 particle in state 2. What else can I do? I can do 1, 1. I can have 1 particle each. Anything else? This is the vacuum state. By definition, right? 0 everywhere. So that's it, right? 4 states. So that's the first tricky thing about many-body systems. The number of particles is not constant. Or it can be constant. You can, put a, you can make your system have a constant number of particles and define that ahead of time. But in general, in many-body system, you can constantly create and annihilate particles. That's what we've been doing for the last 20 minutes. Right? So now you have 4 basis states. This is why, by the way, we're writing the matrix for fermions, because in case of bosons, you can have infinite amount of particles per state. So your matrix will be quite large. That's why we're not going to write matrices for bosons. Okay, so these are the basis states. Now we have to assign vectors to them. I'm going to use the simplest choice that I can make. So I'm just going to use the elementary vectors. To write a matrix on a basis. So there are so if there are 4 states, that means there's a 4x4 matrix. That means there are 16 elements in the matrix. So we now have to calculate the 16 elements when we sandwich A1 dagger between all of these states. So most of them are 0, right? Let's find the non-zero ones. What happens if A1 dagger acts on 0, 0? You get the state 1, 0. So this matrix element is equal to 1. Agreed? But if I put any of the other states as a bra here, it will be 0. Right? And there's one more state that is non-zero. Namely, if I act on 0, 1, I'll get state 1, 1. And all the other matrix elements are 0. And check. This means using the spaces, A1 dagger is represented by the matrix and these are all zeros by this matrix. So a lot of zeros and ones on the -1 diagonal, because this is the way I defined the basis states. So this is the matrix representing the creation operator in state number 1. Okay. Let's move on to a little bit more complicated model known as Schwinger bosons. And this example will illustrate how to think in second quantization. So in QM1, first quantization, you spoke about a particle with spin, so particles have spin. So we're going to think about a single particle, just one particle, and it has spin s, so its states are s, and then there's little m, where m is the z component of the total spin, and of course m is between plus and minus s. So there are a total of 2s plus 1 different states that the particle can be in. And the operators that you can use to manipulate this state are the raising and lowering operators, s plus and s minus. They commute to give 2sz, and sz commutated with s plus minus gives plus minus s plus minus. These are things that you know. I'm just reminding you of some stuff that you know from a long time ago. And you can make a plot of this. So if these are your spin states in the basis Sm, then your spin can be maximally Ss, and then you can go down. This would be state S, S minus 1, and so on and so forth. Let's make this a disconnected plot. And then your lowest state is S minus S, and then here you have S minus S plus 1, and so on and so forth. So this is first quantization. Now I'm going to introduce a list of bosons, or a set of bosons, which will give the same mathematical description for spin, but instead of using one particle with internal structure, I'm going to use bosons with no internal structure. Let me show you what I mean. So we're going to introduce two types of bosons. It's going to be type A and a type B boson. And because these are bosons, I can have a variable number of A-type bosons or B-type bosons. So Na is the number of type A bosons, and B will be a number of type B bosons. And I'm now going to use a mapping, a mathematical mapping, where the state Ss is equal to the state where I have 2s Na bosons and 0 Nb bosons. So 2s A bosons and 0 B bosons. So Na equals 2s and B equals 0. That's what I meant to say. The next state down, Ss minus 1, now I'm going to have 2s minus 1 bosons of type A and 1 boson of type B. Correct. The sum will always be 2s, so I'm going to write that down in a second. This continues, and till I have here 1, 0, and 2s minus 1 and 2s. So first of all, in this system, I am, as was already pointed out, the total number of bosons or particles in general, particles, bosons, capital M, which is equal to Na plus Nb, that is always equal to 2s, no matter which state I'm in. Now, remember your annihilation and creation, not annihilation, sorry, the raising and lowering operators. So what S plus and S minus do, S plus takes you up this ladder, right? And S minus takes you down this ladder. Up to normalization constants, of course. In the same way, we can use creation and annihilation operators to get up and down the boson analog of this system. So we have A daggers that can move, that create A bosons. We have A operators that annihilate A bosons. And the same thing for the B bosons. We have creation operators, B dagger, that create N bosons, going down now because here I'm creating B bosons, and annihilation operators that destroy the B-type bosons. And because these are bosons, we have commutation relations. A dagger equals 1. The commutator of B and B dagger equals 1. And all other commutators are 0. So this is an analog. These bosons may or may not exist in real life. I don't even care about that. It's just a different language. Instead of using the language of S plus, so say I'm in the state S minus S, which is equivalent of having 0 A bosons and 2 SP bosons, I can now move up a state, so to minus S plus 1, by applying S plus. There's an equivalent operator in this system that will do this action. So what we're going to do now as an exercise is we're going to find these operators. So we want to find an expression for S plus minus and SZ in terms of the A's and B's. And then we want to show using the boson algebra that the spin algebra is satisfied. So we have to make sure to choose our operators correctly, because after we map our problem from one description, from one language to another, this is translating from one language to another, they still have to satisfy the same mathematical relations. So we have to make sure that that works. So any ideas? It's basically written on the board already, but how can we write S plus in terms of A's and B's? Right, so S plus is A dagger B. You have to create an A, destroy a B, and that's the same, and that's going up one step. In the same way, S minus is equal to destroying an A and creating a B. It'd be easier to write the other way around, although it doesn't matter because they commute. Now you remember that S plus and S minus are Hermitian conjugate to each other. So that's to still work in the case of A and B bosons. If it doesn't, we have a problem. Does it work? In your head? What's the Hermitian conjugate of A dagger B? So you have to switch the order and then put daggers on all the operators. So it works, right? Okay, that's a good start. What about SZ? How can I build the operator SZ? So if I count the number of A bosons and then subtract the number of B bosons, then I get 2M, right?
We also create from the brackets, from the commentators.
So you're suggesting that you don't know SZ?
No, the one above.
Ah, you want to do this, and get this. Of course that'll work. We'll go the other way around. We're going to guess the operator and then check if this works. Oh, yes, of course you could do that. There's a theorist way and an experimentalist way. Right? You're a theorist, so, you know.
No.
Evidently you are. An experimentalist stares at this long enough to figure out what's going on, right? That's what I did. Right, so this works, right? You count the number here, subtract this number, divide by 2, you get this number, right? Okay, so that was A, now let's do B. Let's check that the commutators work. So let's start with the commutator of S plus and S minus. So this is S plus times S minus. So this is A dagger B, B dagger A, minus B dagger A dagger B. Just written it all out. Now I can switch the order in a few ways. I can't do anything I want because A and A dagger don't commute. But since they're bosons, I don't have to look for minus signs, right? It's the easy case. So I can switch all of the A's and B's as much as I want. So I can group together the A's and the B's. So here I can get A dagger A, B, B dagger. That's legal, right? So I've moved this A to here. And the same thing in the second expression, I can move this B dagger over here. I can do that without worrying about sign problems. So remember what I'm going for. I'm trying to make this look like A dagger A minus B dagger B because I'm supposed to be equal to Z. I'm trying to make this look like this. So I'm already getting closer. Now I can switch this B, B dagger using the commutation relation. This is equal to 1 plus B dagger B. And this A dagger is equal to 1 plus A dagger A. That's getting very close. I already have the A's and B's in the right order for this expression. Now something cancels here, right? So the A dagger times B dagger B minus A dagger B, that cancels, right? So this cancels with this. Read. And I'm left with A dagger A minus B dagger B. Let's look at the definition of SZ. This is twice SZ. So that works. Let's do the second operator, the second commutator. So I'm looking for SZ with S plus. I expect to get S plus again. So this time let's use some commutation relation identities. First of all, let's just take the commutator apart. So I've plugged in SZ, I've plugged in S plus. SZ has two additive terms. So this is the first one, A dagger A, let's take the commutator with A dagger B. And then the second term, B dagger B, again with S plus. And the half is outside. Now what do you do with these awful expressions? So you open up your QM1 homework. And you remember that if you have an expression, a commutator of the form of AB commuting with CD, then you can open this in the following way. You get 4 commutators. I hope you all remember this. For those of you who didn't copy homework 2 years ago, you probably do remember it. For those of you who did copy homework, which I think is at least like 80% of you, probably more. So you just have to believe me. That's now you pay the price. Okay, so we can use this identity and apply it to both the commutators. So we get 1/2 A dagger, AB plus A dagger, B, A dagger, B, A plus A dagger, AB. That's from the first one. And then you get 3 more terms, which all have a minus sign, from the second one. I'll let you figure them out at home. Let me show you what this comes down to. So now you've taken this apart, right? And you now have simple operators, simple commutators. And you can now use the boson algebra to figure them out. So A and B commutator, that's equal to? That's 0, right? A and A dagger is 1. A dagger B is 0. And A dagger is also 0. And in the second row, they'll also all be 0 except for one. The only one that is not 0 is going to be A dagger, B dagger, B, and then B. All the others will be 0. Writing that explicitly when you have the time. And this commutator is equal to, watch out, -1. Right? B dagger is 1. So if you change the order in the commutator, you get a minus sign. This is equal to -1. Let's put this all together. So we get 1/2 A dagger B minus is plus A dagger B. This is just 2 A dagger B divided by 2. This is A dagger B. And this is the way we define our S plus. So it works. Convinced? Cool. Good job. Okay, so what have I done here? I'm not describing any new physics, right? I'm still describing the same particle with internal structure. But what we have shown here is that you can think of this kind of system in this way and the opposite. You can think of this kind of system in this way. So when you see a many-body problem, you might be able to map it onto something that you already know, where you already know the solution, and then you can save yourself the solution. Right? This mapping goes both ways. And in due course, so this, I don't know any application for Schwinger bosons, but there are different mappings out there. Some of them you'll meet, or we will meet in the next few weeks in the course. And one of them we're going to meet next, so in 2 weeks, which is actually used in present research. I've heard people in seminars using this kind of mappings, theorists of course, who use this kind of mappings to solve problems. So this is something that can be very useful if you know what you're doing. Okay, last topic for today. This is one-body operators. I think in class you already reached two-body operators. We're going to reach two-body operators 2 weeks, because two-body operators are automatic interactions. So everything we're doing today is still without interactions. But I'd like to demonstrate to you how one-body operators work in second quantization, the language of second quantization. This is something you have to get used to. You'll have time to exercise between now and in 2 weeks' time at home as well. And then when we know that we have this, we know how to use this formalism, it'll then make it much easier to do real-life problems. So with interaction. Okay, so let's start again with first quantization. So there you had operators, which in general I'll just call F, and we had single particle states, which are given by quantum numbers, which we call lambda. And let's assume that lambda is the basis in which F is diagonal. So F operator is diagonal in basis lambda. We can always find a basis in which a single particle operator is diagonal. If you don't remember how to do that, look 2 years back and don't copy homework. So this means that the operator acting on state lambda gives you some eigenvalue, which I will call F lambda, acting on this lambda. That's by definition what a diagonal basis means. Now, what happens if we have a many-body system? So in the many-body system, we can use the same operator, but now we have to say on which of the particles this operator is acting. So this could be, for example, the momentum operator. So if you only have one particle, then obviously you're trying to measure the momentum of that one particle. You're not going to measure momentum of something that doesn't exist. But if you have a many-body system with a million particles, you have to specify the momentum of which particle you would like to measure. So in this case, the operator has an index j, where j symbolizes on which particle you're acting. Acting on the jth particle. And if you now want to act on the entire state, so you want to measure the momentum, so the momentum of the entire system, right? Because you're never going to be able to look microscopically. Well, how do you express the operator of the entire system? So you have to measure the momentum of all the particles and then sum over all the particles. As simple as that. This is not necessarily something that you can do in an experiment. You cannot go to every single particle and ask it, hello, what's your momentum? But in general, if you think of the formalism, this is what you have to do if you want to know the total momentum. You have to go and measure each individual momentum and then sum over all of them. Now, if this acts on a Fock state, so F acts on a Fock state N1, N2, N3, and so on, and you know the eigenvalues of the momentum operator, again, we're on a diagonal basis, then this means that what you will get is just the sum over all this J, the sum over all eigenstates, eigenvalues times the number of particles in that state, right? Because this by definition means that you have n1 particles in state lambda 1, n2 particles in state lambda 2, n3 particles in state lambda 3. So in the momentum, if you want to use the momentum example again, n1 particles have momentum p1, n2 particles have momentum p2, n3 particles have momentum p3, and so on. That's what this means by definition. So if you're now trying to find the total momentum, well, you have to take the momentum f1, p1, multiplied by the number of particles in the state p1, and then you sum of all particles. So this works if you can write f in a state in the diagonal state, if you know the diagonal form. But what if you want to write this in a state which is not diagonal? Say you want to write the momentum operator. So the momentum operator is just the numbers fj times the number operator, which is a dagger a. What if it's not diagonal? What if f hat is not diagonal? What if? So what if I want to represent this operator in position space? So what this means in thought experiment, I don't want to go to each. What I'm doing here is I'm going to each particle. I don't know what a particle is. I'm just saying, shouting out particle number 1, what's your momentum? And he shouts back at me P1. And I ask particle number 2, what's your momentum? And he shouts back at me. But what if I want to do something else? I want to go to position x1, check is there a particle there. If there's a particle there, I'll measure its momentum. I'll write it down. Then I'll move to position x2. Now I'll check if there's a particle. I'll ask what's your momentum, and so on. So now the momentum operator is not diagonal anymore, right? So so how can I write this operator in a non-diagonal basis? Yeah.
In the second line, there's the off state in the.
Yeah. So if I'm working in a non-diagonal basis, say in position. So now I need to use the operator psi dagger, then the operator f, and then a psi, where the psi without a dagger annihilates a particle at position r. And this thing here creates at r. So for example, if I want to use the Hamiltonian, let's think of a non-interacting system, in which case the Hamiltonian is equal to the momentum squared over 2m plus the potential. And single particle operators are usually written with little letters. So we used to call this capital H, Hamiltonian, but since it's the single particle operator, I'll call it the little h, and then the total Hamiltonian, which is the energy of the entire system, the sum over all particles. If I want to write this in position space, this is sum over all of space, psi dagger, position r, and then the operator p squared over 2m plus v of r, and then psi. Correct. Yes, it is an R on X, sorry.
So it will be in different places. You create in one place and
I think that's a mistake. On one particle operator or two particle? On two body operators, you might have different spaces. One body? For one body operators, it's the same place. And I'll demonstrate why in a minute as well. I'll make an example and I'll demonstrate why this works. And then I'll come back to the script as well. But of course, it's not diagonal, and in diagonal form, you've seen this before, the energy or total energy in diagonal form is sum over all the single particle energies, A dagger A, sum over all particles. So here I'm using the position basis, and here I'm using the eigenbasis of the single particle Hamiltonian, which in this case are also the eigenbasis of the many particle Hamiltonian, but next time we're going to add interactions and this will not be diagonal anymore. But for now it is. So this sounds a little complicated. Let me do a example to demonstrate how this works.
So the second Hamiltonian, the one with the sum,
Yeah, diagonal.
is the red.
Right, because this you can, if you know your Fock state, it's easy to figure out the energy from here. Right, it's diagonal if you use Fock states. Let's think about spin operators. We're going to think about a system with n particles. So we have n spin 1/2 particles. So if you think about the single particle system, if you only have one spin, then the spin operators, this should be a little s, not a big S. The little s spin operators are equal to the Pauli matrix divided by 2, or if you want h bar over 2 times the Pauli matrix, where the Pauli matrices are, I hope, more or less known. And so now we can try writing down the total spin. So this is a capital S. And let's try the operator SZ. And we'll follow this idea of putting a integral and sandwiching the operator between an annihilation and a creation operator. But because spin is discrete, we don't have an integral with a sum. So what we get is h bar over 2, sum over alpha prime and alpha. These are two indices. Sigma z alpha prime alpha. Okay, this is what you meant, right? Now I have different indices. In position, you must have the same index because the operators cannot destroy a particle in one place and move it to another place. If you find something that can do that, it's called teleportation. And, well, we've only succeeded to do that with photons up till today. And also that wasn't really moving the same photon, it was copying the quantum state from one photon to another. So if you find a way to do that with R and R prime, let me know. Or just tell the Nobel Committee. But in spin spaces it's possible. And to demonstrate how this works and why this works, we're going to now act with SZ on a spin-up particle. So alpha and alpha prime are indices that are equal to 1 or 2 in the matrix, or equal to up and down if you want to think in terms of spins. So we're going to consider a system with one particle in state up, so n up is equal to 1, and 0 particles in the state down. So the Fock state is just written as 1, 0. n1 is equal to 1 and n2 is equal to 0. And let's try and find out what is the total spin in the system. So we're applying SZ, capital S, the many-body operator, and we're acting with it on the state 1, 0. This is a many-body or a second quantized expression. I'm sure that you can all solve this problem in first quantization. You can all figure out what is SZ if you have a spin-up particle and no spin-down particles. It's not very difficult. You get plus h bar over 2, right? But let's see how this expression does this, how this works. So let's just do it step by step. Let's plug in our operator. It's h bar over 2 sum alpha prime alpha a dagger alpha prime. Then there's the matrix sigma z alpha prime alpha. And then there's an annihilation operator. And this is acting on 1, 0. So let's start by doing the sum over alpha. Right, there are two sums, one over alpha, one over alpha prime. Let's start summing over alpha and see what happens to this expression. So there are going to be two terms here, right, when you do the sum. There's going to be a term A1 or A up 1, 0, and a term A down 1, 0. What does the first one do? So this thing destroys a particle in the up state, right? So this will give the state 0, 0. And what about the second one? Now destroying a particle in the down state? The number 0 or the state 0? The number 0, right? So out of this sum over alpha, there's actually no sum, it's only one term. Right? So we've done this sum, let's write down what we get. This is h bar over 2. I'm still left with the sum over alpha prime. So there's an A dagger alpha prime, sigma z alpha prime. And what about alpha? It must be equal to 1 because it's equal to 0. The entire term is 0, right? And here I have the state 0, 0. But there were two terms, one of them is 0, this is the other one. Okay, now let's go to our Pauli matrix. We know that alpha, the second index, is equal to 1. We're using sigma z. Second index equal to 1. The other way around, right? Second index is 0 to 1, which means we're in the first column. We're in this column, right? So if alpha, and now alpha prime can be equal to either 1 or 2, right? If alpha prime is equal to 1, then this sigma z matrix element is equal to 1. And if alpha prime is equal to 2, then the matrix element is 0. So again, this sum is simple. There's only one term which is non-zero. Only alpha prime equals 1. So now we get h bar over 2. Alpha prime is equal to 1, so we get a dagger acting on 0, 0. And the matrix escapes a number 1, which is irrelevant. And now what happens if A1 dagger acts on this state? We just get back the state 1, 0. So 1 particle in the up state and 0 particles in the down state. And this, of course, what you expected. If SZ acts on the state with 1 particle in the up state and 0 particles in the down state, you get back the same vector, the same state. And the value of the spin up. The answer was obvious. But this happened, and notice that during the calculation, we found ourselves in a different state, right? But this brought us there. So this lets us think. This actually illustrates how we should think about operators in second quantization. So let me illustrate this again with this example. I'll take you through step by step, and then I'll show you how this makes sense also in the position basis. So on the right of an operator, you start with an annihilation operator. What the annihilation operator does, it's like a metal detector. It goes around and it looks for particles. Because if there's no particle, this is equal to 0. Only if there's a particle, then it says, okay, there's a particle here, you have to do something. And then it beeps, right? And it automatically takes this index, right, and puts into here. Now the single particle operator does its job. It figures out what is the spin at this location, what is the spin of this particle. And after that, you have to put that particle back. And that's exactly what this means as well. So you're moving around, you're looking all around space, and if there's no particle, this will always give you 0. Only when you detect the particle beeps up, you measure the energy, momentum plus kinetic plus potential energy of the particle at that position, right? And then after that, you have to put the particle back because, you can't just get rid of particles. So you put the particle back, you leave the system unchanged, and the integral tells you that you have to sum over all space. So you're looking around the entire world, looking for particles, and putting the energy. Okay, but this was still a simple example. We still have a few minutes. I still have 1 minute. Okay, so in the last minute, let me do a little bit more complicated example because the example with SZ was still diagonal, right? So alpha was equal to alpha prime. I didn't actually do any change. What happens if I act with SX, for example? So the total spin operator in the x direction on this state, on the state 1, 0. So what I would like to evaluate is Sx, which is equal to the same operator, but instead of using z, I have to use x here. So Sx acting on the state 1, 0. This is one particle in the state up, and 0 particles in the state down. So this h bar over 2 is sum over alpha prime and alpha dagger alpha prime, sigma x, alpha prime alpha acting, and then a alpha acting on 1, 0. So this is a demonstration of an operator that is not diagonal. The bases, A and A dagger, create and annihilate particles in the basis where SZ is diagonal. But the operator is sigma x, which does not commute with sigma z, so it's not diagonal, right? So this is the more general version and a little bit more complicated version. But what do you expect to happen? Think of QM1. What happens if you have a spin up and you act with SZ? What happens? I'm kind of demonstrating it. You flip the spin, right? Right? No? Yes? I think we flip the spin. Who agrees? Okay, so let's see how this works in second quantization, right? Let's see this happen if we do this step by step. Oh, here I wrote in your homework, you will show. Let's do it. So I'm going to get h bar over 2. So when the first step is the same as above. When A alpha acts on 1, 0, only alpha equals 1 contributes. So we have sum over alpha prime A alpha prime dagger sigma x alpha prime 1 times 0, 0. Right? That's the same as above. I've used the annihilation operator. I've detected a particle in spin up. I've detected 0 particles in spin down. Now I have to go back to my matrix. Now if alpha is equal to 1, again I'm in this column. So alpha prime equals 1 does not contribute, it's 0. And now only alpha prime equals 2 contributes. So you get h bar over 2 A dagger 2 times the matrix element, which is, let's write explicitly, sigma x 2, 1, and this is just the number 1, it's right here, times the state 0, 0. And now you can act with A2 dagger on the vacuum, and you create a particle in the down state, so you get h bar over 2, 0, 1. What you have done here is you have acted on sigma with sigma x on the state 1, 0, and you have obtained the state 0, 1. Okay? So in first quantization, not till now, you thought a spin flip of the same particle. It started like this and somehow became this. And you don't really care about what happened in the middle, but it's the same particle. In second quantization, the language is totally different. What we're saying is we started with 1 particle in this state and 0 particles in the other state. We have annihilated the up state particle and created a down state particle. It physically means the same thing, right? But the way we think about these systems is different. And that's what I'm trying to illustrate. Everything clear? Simple, right? It's always simple. Questions? You're shocked. Okay, so enjoy getting into this, and in 2 weeks' time we'll start adding interactions and getting really heavy stuff.